Okay, next we go and take a look what this quantization stuff actually means in case of this Matlab or Octave, whatever you are using. Oh, I should actually use the Matlab now because of the toolbox. If you are using Octave, don't. Last time I already gave you some instructions how to get this free trial version of Matlab for your own computer so you can actually do the exercise. Yes, this exercise can be done without it, but it will be so much easier to do it with. And we have this Matlab version has, the classroom version has the required tools for studies. Okay, so basically the exercise goes like that. So there's first the bandstop notch filter. Okay, the same as on the previous fifth exercise, I think, about the same. Yes, it's the same task as in exercise 5. Okay, these, well, the sampling, check the sampling rate and other requirements. It might be a little bit different. Okay. But anyways, you do the design by that, but you know how to do it. Then determine the filter coefficients and compare to original floating point and new fixed point system responses, what happens to stability and such. About 30% of you will get unstable system. Yeah, so if you get unstable, just recognize it and give an answer. All right. But it also means 70% of you will still have a stable system. Then there's the bandpass filter to match the following properties and determining how many bits should be used. Okay, yep. How many bits again, and so on. Okay, how many MAC operations? Ah, this is so much fun. Oh, right. Hey, wait a minute. Which processor you are using on the embedded systems programming part? It's ARM. Yes, good. Excellent, even better. Yes. Oh, I guess it's M0, right? Well, M3. Oh, okay. But it doesn't have float. That's excellent. Yep. How many MAC operations the previous SOS system takes to calculate on a single step on fixed point platform? So you have fixed point. Okay, and then okay, let's see. Channels. How many channels? Running at which 130 megahertz. 120. Okay. Okay. Now it fits into your requirements. Okay. So basically it's your platform. Calculate the how many channels you can in theory run on the M4. One way of doing this calculation approximation is basically to test it. I used to have the test in here. So if you feel like it, make a simple second order system and run. See how many operations you can do on that one in 1 second, and the rest is simple calculations. Okay, and then there's a measure the play performance of your laptop and estimate how many channels it can handle on Matlab or laptop or these computers here. So basically everything comes from the fact that you need to know how fast the calculations are done. I will show you some examples how you can do it on Matlab. It's quite simple, and actually it's almost as simple also on your development environment. So it's basically just you have a let's see what it is, CPU time. You have a function that gives you current CPU time in milliseconds or whatever the unit is for your platform. You take the current time, then do the calculations, and then you take the current time again, and the basic just the difference, calculate the difference. It's simple. It's called engineering. Yeah. Okay. Not Octave. Matlab. I have the free version of Matlab here for 2 more weeks. All right. So let's see. Let me delete some of that. That is last week. Okay, and current folder. Yeah, folder 6. Okay, so quantization is the name of the game. And what it is basically, okay, how to do the quantization the old-fashioned way, the hardcore kind of stuff. If you have some filter coefficients, let me take, for example, just for fun, I've checked the Butterworth filter, second order. Okay. Oh, help. Design specification, second order. Second order, and then is it 0.5? See, does it give me? Oh, okay. It gives me some numbers. So, and the sampling rate, for example, just 2 kilohertz. Then the frequency response for this one would be BBA 1024 FS. Let's see what that looks like. Yeah, it looks like that. That looks like Butterworth design. Oh, yeah, that's funny. Looks a little bit funny. I don't know if there's anything to. Okay. Anyhow, so if you want to calculate the approximate basically the quantization effects for floating point system, you start from the floating point system and take a look at what is the minimum and maximum of those values. And I would say all of here is within plus minus 1. And then we take a function called quant. So basically we can quantize those values by giving the minimum quantization step. Meaning that, for example, BB quant equals quant of BB, and the size would be 1 divided by 2 to the power of 7, for example. So plus minus 7 bits, meaning 8 bits in total. Since we had plus minus 1, the range. for values. So this is the 8-bit quantization of those values. Okay, so we got some difference probably. Well, yes, we actually did. So let's see, BB minus BBQ. So we made this size error by quantizing those values. And let's do the same thing for the AAQ quant of AA 1 divided by 2 to the power of 7 again. There we go. I think we got some other stuff there. Okay. So we have, okay, well, that's it. This is 10 to minus 3. We have some difference from between those values. Let's take a look at what this does for the zeros and poles. Not much actually. Since secondary system, it doesn't really do that much, but just for fun. So CCQ equals roots of BBQ and ZZ is roots of BB. So quantized and non-quantized did the zero locations. Let's see how much these zeros actually are different. I'll do something that never should be done, but well, I'll actually give the other zeros as poles. All right. Okay, there you go. So the real zeros are right here. The 8-bit quantizing of that filter moves these zeros. They are not anymore giving the highest possible attenuation of that angle. It basically gives something. Yeah, it actually affects quite a lot for the performance. You don't get much of the attenuation anymore, or not that much. Maybe something like 20 dB or something like that. Same thing for the poles. Same thing for the poles, but the poles seems to be actually quite at the same place, not exactly. So basically, it affects on the stop band attenuation of the filter. Not that much on the pass band, but on the stop band attenuation. And of course, I can. Let's see. Frequency response with the quantized parameters BBQ, AAQ. Yes. So we get about 45 dB of stop band attenuation instead of that infinite stop band attenuation of the highest possible rate. Okay. So yes, this quantization definitely has some bad effects on your design. How to avoid those errors? Well, minimize the errors. You cannot avoid them. You always have them. You just have to deal with it. So basically, what would a professional do? Professional would start a filter designer on Matlab. Does not exist on Octave or any other platform. There. So basically, did we use this one already last time? Yes, we did. on same as IIR design. Okay, let's see. FSS by sample rate, say 200 hertz, stop and starts at 300 hertz. Design that filter. There we go. Direct form FIR would be like that. Okay, let me go and do this one. How about the quantizing it of the third box here from top? Set quantization parameters. And life gets much easier. Well, on the filter design part. Not more than that. Okay, so currently we are doing the calculations using double precision floating point. But we can also do some other. Single precision floating point? Yes, there are some coprocessors for single precision floating point. And yes, some of actually the floating point processors can do single precision twice as fast as double precision as well. Splitting, basically, those are basically just cutting the those very long words into two shorter words. Okay, but anyways, I'm really interested about fixed point. Okay, you have this feature there on the computers. I don't. In my demonstration, it does not show up. I didn't know that. Sorry about that. But anyways, you can do some of that stuff there. I will move into the classroom computer. Unfortunately, this does not show up on my video then. But well, too bad. Yes, as kind of yeah, expected. Yes, so I will actually as soon as that one starts, I will turn into the all right, so nothing to see anymore on the video stream. I'll just close that